Hello guys, welcome to this sixth part of the assembly series, and finally we are in the position where we can finally have a look at the assembly code. This is the code, this is not much, and actually try to make sense of it, right? But before doing that, let's actually see what we're trying to do, alright? So this is the Maya plugin, alright? So it's the deformer, is actually pushing on the normal. It's not a translation on the transform. It's actually pushing the normal. And we can see that by, let's grab a vertex. Let's increase that. All right. Right. So I have, oh, nice. What are the colors? I have no idea. All right. So I pushed up and make a spike, right? And now if the push node, I change the amount, you see that the part which is flat is pushing upwards because the normal is upwards. The other, so the spike is increasing size because I'm pushing outward the normal, and here is freaking out downstairs because it's pushing against the same mesh, right? So that's the behavior of the node, right? So that's what happened. For any, I don't know why, for some reason my screen won't go faster than 60, so like the Maya viewport either. So my monitor is 60 FPS, but the viewport should be go faster than that. pt6 is off, so I have no idea, but honestly I don't care. It's not a matter of performance here, right? So that's what the node does. So it grabs the normal, it scales the normal by the amount we tell here, so in this case 0.5, and we sum this vector to the original vector. That's the final position. So super simple. We can actually see that in the Maya code, right? So this is the original code. This is the original code using pointers. If you actually want to see the one using Maya API, right? That's it. We grab the normal, we cast it to m vector, we scale by the envelope and the amount, right? Which we can just call it, I don't know, like double weight. I think in the order I do it, I pre-multiply the weight, so it doesn't matter. So we scale it and we sum it to the current position. That's it. That's how the plugin works. So here there is the actual call to push no stress loop, which is the procedure we are defining here. So this is actually our assembly function, right? Which is defined in the header. So if we select it, press F12, here I have a assem.header where I define all the different assembly function I'm going to call. So this case is the most simplest one. And we are going to pass in the points, which is a double pointer, the normals, which is a float pointer, the weight, which is just a double, and an integer say how many points we need to process, right? And that's the only thing we need. So you might wonder, where do you get this double pointer for the position? Where do you get this float pointer? So let's actually see where I do get that, because we are kind of hacking the Maya containers, right? So I extract the position the usual way. I have the iterator, I say, hey iterator, give me all the position, and store into an endpoint array. Then I grab an MFN mesh and I extract the normals. Here we go. MFN mesh, get normals, and I have an m float vector array, right? So here what I do is I access the first element, right? The x value, so it's the first element ever in the container, and I grab the address, right? So the ampersand here is the address. I do the same exact thing for the normals. Now, if you have a bit of problem understanding what's going on here, let me try to write that really quickly. So I'm using my mouse, so we need to suffer for my horrible writing. I'm not using my surface. So let's say this is our container, right? So our endpoint array, blah blah blah. You know what I'm writing here. So MP is fine. If I grab the address of this, right, basically I grab the pointer in memory where the start of the class, the instance is in memory, right? So that should be, I don't know, 0x, 0, 1, 2, whatever, right? Doesn't really matter. So if you just grab the address of pos, right? So of the endpoint array, this is not where the data is, right? Because the endpoint array is a resizable container, right? So it's an abstraction that makes you resize arrays easier for you, because in a computer, a resizable array doesn't exist, right? It doesn't exist because you have no guarantees that when you go ask for more memory to the operating system, that the operating system is able to give it to you. Actually, it doesn't even try, right? So internally of the container, right, you just have a pointer to where the actual memory is, right? This is actually where our x, y, z, blah, blah, blah positions are, right? And what happens when you want to have more memory, you want to push another point, and you don't have space? What happens is that the endpoint array for you is going to allocate other memory, like bigger memory, right? And is going to copy this memory here for you, right? So you get as much of this free memory, so you can add more stuff to it, but you're just manipulating the endpoint array. So for you, nothing changed, right? You're not looking at the data itself directly. You're using the endpoint array abstraction, right? So for you, nothing changed, but that's what's actually happening here. So if you want to access the data, right, you want to grab the address of the first actual element. So when you access the first point, the x value, right, you're accessing this. And if you grab the address, I don't even know how to write an ampersand, whatever, you're actually grabbing the address of the first element of the data, so that you can just shift and you have all the others, right? So that's what I mean by hacking the Maya data structure, the Maya array. And vector, the standard vector works exactly the same way. He's an indirection to where the actual memory is. So by accessing the first element, the x value, and then grabbing the address, there we have a double pointer, right? You can put parentheses if you like it, right? It makes your life easier. So the same for the normals. Now, we need to be careful, because an endpoint is actually 4 values. It's x, y, z, and w, right? You don't access the w, but you have it because it makes life easier for matching multiplication and other stuff, right? So also, like, it's easier on the cache of the processor and whatever. So you actually have your data x, y, z, w, x, y, z, w, right? So if you want to shift by 1 point, right? So to access the second x value, you need to shift by 4 values, right? Instead, the normals, sorry, you need to shift by 4 doubles. And you will see that that makes a massive difference, right? Instead, the normals are just 3 floats, right? You see that because it's a n float vector, so you already know there are float, and then by investigating it, I found out that basically it's padded tree. So you have x, y, z, x, y, z, x, y, z. So if you want to jump to the second point, you shift by 3 floats. And that is going to be extremely, extremely important when we jump in the actual code. Okay? And finally, then we multiply the amount in the envelope, and that's going to be our weight. So we don't have to multiply that all the time, so we pre-multiply that. And then we pass count, which is nothing more than the point count, right? So this is not the amount of doubles we have in the array, but this is the amount of points, right? So this value is actually number of doubles divided by, I think, 4. Yes, 4, because it's padded 4, right? So it's the number of points. Right, so in order to not make the video too long, I'm going to stop here. And in the next video, we are going to finally put hands on the actual code you see here. We are going line by line, explain everything, and see how stuff works. All right, so see you in the next video, guys.